ల్యాప్టాప్ ఇస్తావా?
Hello students, today's class we'll solve one more numerical on this theories of failure, one more numerical, and then we'll move on to our final topic, that is stress concentration, right? So check out this numerical problem. We have a machine member made of C40 steel. Material is given having a yield stress of 3 to 8.6 megapascal. So yield stress is given. So sigma y, which is the yield stress, is 3 to 8.6. This is given. This is our data here. And we have axial stresses given. So there are three separate cases. You have sigma x as 40 and sigma y 20. Similarly, you have sigma x and tau. You have sigma x, sigma y, and tau. So this is similar to biaxial with shear, and biaxial with shear, and uniaxial with shear. So you have three different cases which you can find the values, and what is required to be found is you need to determine the factor of safety. Okay, this factor of safety value we need to determine using the theories of failure. Okay, for each loading condition, you have to devise a method so that you need to find for the factor of safety for all these cases. Okay, so let's see how we can do this. I'm just going to copy this question over here and or paste over here, and right, so we can start off now. So first off, let's see what all theories of failure are in consideration. So for this numerical, let's consider the three which we have already discussed. That is, number one, maximum principal stress theory. Stress theory. And the second one is maximum shear stress theory. And the third one is distortion energy theory. The distortion energy, or you can also call this as von Mises. So most of the companies, they ask interviews in the form of von Mises or von Mises theory of failure. You can call it in that way. So first problem, okay, first case, that is A. You see sigma x is given, sigma x and sigma y. So what is the objective here is to find the factor of safety. So we need to determine the factor of safety. So in this case, it is a biaxial case. You see case A, if I want to write down in a 2D kind of a plane, that is subjected to axial, a biaxial stress case. So you have sigma x here and you have sigma y, right? So in a biaxial case, you have both which are acting in an axial direction, 40 and 20 megapascal. Okay. So among these, you just identify whichever is maximum. So here, sigma 1 sigma x or sigma y. Okay, it's pretty straightforward. You can see that sigma x is greater in magnitude. So 40 megapascal or 40 Newton per meter square is greater in magnitude, and there is no shear component. So therefore, according to the first theory, that is maximum principal stress theory. I'll just write principal stress theory. So according to maximum principal stress theory, it is just that sigma 1. Sigma 1 will be maximum, that is equal to sigma x. Okay, so sigma 1 is equal to sigma x, and I can just write sigma y by n. So this is the safety factor, right? Yield over the factor of safety. So I can denote it as n or FOS, so whichever you feel is suitable. There is sigma y over FOS equal to the maximum stress, sigma 1. In this case, you won't get the entire formula. Why? Because you don't have a shear component over here. So it's only a biaxial case without shear. So therefore, equate this directly to sigma 1. Okay. So let's solve this. So if we solve this, you get sigma y, that is yield. So here you might get a little bit confused. So sigma y, I'll change this to yt. So here y means yield stress or yield tensile stress. Sometimes it is called. Okay, so let's write yt over here. So don't get confused. Sigma y is axial, but it is yt. Okay, so this sigma y is different and sigma yt is different. So yt is yield tensile strength. So it's a material property. So this property will be given. So for that particular material, it means that it is the maximum amount of force or stress you can apply on that particular material, right? So you just change that to yt. So it's just yield tensile strength, yt means. But the maximum stress remains sigma x, because in magnitude this is coming to around 40 and this is 20. So therefore, in magnitude, sigma x is greater. So that's why we are equating sigma 1 to sigma x, since it's only biaxial case. Okay. So sigma y here given is 328.6 over factor of safety is equal to sigma x, or sigma 1 is 40. So straightforward factor of safety we can directly find using this above equation. So this is according to the first theory, that is maximum principal stress theory. Suppose we use the second theory, that is maximum shear stress theory. Okay, let's use let's say maximum shear stress. Shear stress theory. Okay, so then again, what is shear stress? Tau max. Tau max we have to equate to the maximum stress, that is sigma 1. So this is the maximum stress. There is no shear. This is the maximum stress we are encountering. Again, according to this theory, what is tau max? So approximately tau max can be given a relation of yield stress divided by 2 into factor of safety. So this is again a standard form in which how you can write what is the maximum stress. And maximum stress which is experiences here sigma 1. So similar to what we did in the previous, just equate. So sigma yt is 328.6 over 2 into factor of safety equal to sigma 1, which was our maximum stress, that is 40. So again, with this, you will get what is the allowable factor of safety for this particular material here. Okay, so according to principal stress theory, you may get one factor of safety. Let's say, let's divide this. If you already divided, you can post it in the group chat. Is this 3 to 8.6 divided by 40? So this is giving me a factor of safety of 8.215. That's the factor of safety. Then suppose considering this maximum shear stress theory, there's half of that. So factor of safety is 4.1075. So you can see how drastically it has reduced. And the more the factor of safety means, more is your what do you say? The material. More is your material requirements, then more is the weight and all those things. Okay. So moving on to maximum, that is the distortion energy theory. So if you take distortion energy theory, you need to consider both maximum and minimum cases here, right? The third case, distortion energy theory. So distortion energy theory is given by, again, standard equation, and you need to memorize this particular equation, that is sigma maximum, that is YT over factor of safety whole squared is equal to sigma 1 squared plus sigma 2 squared minus sigma 1 sigma 2. Okay, so this is the maximum value of stress which we will be encountering, and it is not YT. This will be the maximum stress. Is not the factor. Let's make this as maximum. You can substitute all in once. No, not a problem. So let's do this. So this is 328.6 divided by the factor of safety, the whole squared, is equal to, here sigma 1 will be the maximum, that is 40 Newton per mm squared, and sigma 2 will be 20 Newton per mm squared. Okay. So this can be written as 40 squared plus 20 squared minus 40 into 20. Okay. Solving this, we'll get our factor of safety. What is our factor of safety? So let's do it first. Sending square to the other side and square root of this whole thing. You can just imagine, I guess. So let's say 40 squared plus 20 squared minus 40 into 20. Square root of this, and 328.6 divided by this answer. So if you calculate, you get factor of safety as 9.4859. Okay, so this is what you get, factor of safety using the distortion energy here. So in this same fashion, we'll be required to function for all the three cases here. Okay, suppose second one, that is including the sigma x and sigma y. Okay, so in this case, we'll need to find since there are shear components, we'll need to find first using the principal stresses equation, the maximum and minimum stresses. So I'll skip the second one. You can practice that, and I'll do the third one. I'll tell you how to do the third one so that you can easily perform this operation on the second one. Okay. So I'm taking this third case. So check this out. You have biaxial stress with shear. So you have a component like this, and for this component you have biaxial. So you have sigma x and you have sigma y, and also you have shear components. Oh, this is like so. Do be careful while drawing. So sigma x is axial. You can see this is sigma x, whereas sigma y is compressive. Okay, sigma y is negative, therefore it is compressive, and shear stress is positive, so we'll put it on the positive quadrant. So that's our positive quadrant. That's tau xy. So in this problem, you have shear also. So if you have shear components also, it is always advisable to find using the principal stress equation. Using the principal stress equation. Let's solve this. So we need to find first the maximum and minimum stress, that is sigma 1 and sigma 2. The maximum and minimum stress are required to be found before we go into the series of failure and also finding the factor of safeties. Right. So let's do that. Sigma 1, how do we get? So sigma 1 comma 2, we already defined this many times. It is sigma x plus sigma y by 2 plus or minus under the root sigma x minus sigma y by 2 the whole squared plus tau xy squared. So that's our shear stress, that is the principal stress equation, which we have performed already many number of times. Right. So let's start off with this. So just substitute, plug and play. So in the part in the B, this is C, which what I'm doing. There is a third part. Second part of this this problem, you don't have to put this y. Okay, it's only by axial with shear. So these y components, they get eliminated, and the problem is simple. That is case B. You can try it out on your own. I'm doing the worst case problem. The B1, that is the second one, you can do this on your own. So x and tau xy are given, and both are positive. You can try this out by yourself. But sigma x, you see, here in the third case is the worst case scenario, so I'm doing this problem. The first thing, always find the principal in problems like this. So sigma 1 and 2 can be found out using this. So sigma x is 60 minus sigma y is 20 over 2 plus or minus under the root have 60 plus 20 the whole square plus tau xy is 30 square. So let's solve this equation. You get 40 by 2 is 20 plus or minus. Solve that also. We'll get let me do that. 60 plus 20 over 2 squared plus 30 square. The root of that is you get 50. Right. So sigma 1 comma 2 is we'll find out individually. let's say sigma 1, the maximum stress equation. So sigma 1 is 20 plus 50 is 70 Newton per mm squared. Yeah, right. 70, and sigma 2, the minimum stress is 20 minus 30 Newton per mm squared. Okay, so now that we have found out sigma 1 and sigma 2, our problem is simpler. So this sigma 1 is regarded as our maximum stress, sigma maximum stress. Okay, so we can start off now. So first one is, what we have is this maximum principal stress theory. Okay, so let me just copy this. Just make it for it.
जयेश हमें काम से कर दो
The maximum principal stress theory. According to maximum principal stress theory, it is sigma y t, that is yield tensile stress, over factor of safety, is equal to whichever the maximum stress is, sigma max. So in this case, it is sigma 1, right? So let's substitute that. So you get from this, it is sigma yt 3 to 6, I think 6, 3 to 8.6. This is 3 to 8.6 over factor of safety is equal to sigma maximum. What we got here was 70. So therefore we can find what is the factor of safety here. Okay, so similarly, using the second one, this is the maximum shear stress theory. So according to maximum shear stress theory, we have tau max, right? So the standard equation which we defined, but here it is related to sigma 1 and sigma 2 both. Okay, sigma 1 and sigma 2, as we saw in the previous problem. So once we find the principal stresses, or problems becomes easier. You don't need to find tau max for that. So tau max is equal to sigma 1 minus sigma 2 by 2. So that's the equation for maximum shear stress. So we have tau max also can be written as sigma yt, yield stress, by 2 into factor of safety, is equal to sigma 1. What is sigma 1? Is 70. 70 minus of minus 30, you get plus 30 divided by 2. So again, this will give us a new value of factor of safety. So again, we get a factor of safety, another value from this, and finally maximum the distortion energy theory. This thing, distortion energy theory. Okay, this is the third and last part. So distortion energy theory again given by this particular equation here. So it is always advisable to do this, finding the principal stresses first and then solve it. So let's do this. The sigma yt 3 to 8.6 by factor of safety, the whole square, is equal to sigma 1, that is 70 squared, plus sigma 2 30 squared. So since it is negative, it turns positive once you square it. And for this, it's 70 into minus 30. Okay. So again, from this you get the factor of safety. So let's find out the value one by one. What is the factor of safety here? The factor of safety is an important parameter because that's what determines your dimensions, right? So 3 to 8.6 over 70. Yeah, you're right. So it is 4.694, and tau max. Okay, what you got is 3.28. You're right, and the last one is 70 squared plus 30 squared minus, or you can say plus, and 3s are 2100, and square root of that, and 3 to 8.6 divided by that. So almost a very close value of factor of safety you get. If I calculate this, you get a value like 3.697. So somewhere around this value you get. So just try to find this value. So distortion is the theory, you see, it is a little bit stringent than the first one, that is principal stress theory. Using principal stress theory, we got 4.694, whereas using the shear stress theory, which is very stringent, we got a value of 3.28, and using the distortion energy theory, you got a factor of safety of 2. So each decimal point will contribute to adding material, adding values to the whole part, or whichever element you are designing, So therefore, it is important to very optimize this value for that particular part. Okay. Right. So with this, with theory of failure numericals are done. So I'll quote some numericals apart from what I have done. So next, let's move on to the next topic. The next topic is stress concentration. So stress concentration, okay, is as the name itself indicates, it's a factor. So sometimes we'll take this stress concentration into account, so that it needs to be some, check out this example here. So check out this example here. We have a bar with a hole, a plate with a hole, which is axially loaded. You're applying some force here, and at this cross section, so the material will fail starting from this hole here. So how this will fail is, you need to find exactly what is the cross sectional area. So what is the exact cross section area of this part is load P divided by P into D. So this breadth into the depth. So this subtracted by that diameter here. So B minus D. So this is the breadth here. So that is subtracted by this diameter. So the cross section area is just, you subtract the diameter and multiply with the height. So that is the subtraction you do here. So why? Because only you want that particular area in the cross section. So if I were to draw this, so you just get the cross section area, which is like this. So that particular section, so that load is taken care only by this area here, so this hatched area. So this is nothing but the diameter of hole. Okay, if you see the side view, no, this is how it will look like. That's the hole. So only this area it takes off all the load which are applying. So therefore, if you perform a concentration here, you can see the pressure in the inside of the hole is greater. So because of the discontinuity, the pressure acting at this inside portion of the hole is greater than the outside one. So that's where the stress concentration factor KT is defined. So this is defined as maximum stress over average stress. So average stress is the stress encountered at the least cross section area. Okay, so this is encountered at least cross section area. Okay, whereas maximum stress is the usual cross section area, that is without the discontinuity. Say without discontinuity. So without discontinuity, whatever value you encounter, the stress you encounter, so that is determined as the value, the actual value of that. Okay, so that's how it works. You have that stress concentration means the stress concentration factor whenever there is any discontinuity uh, in the part. So that time you consider that. Right? So this is not true only for plate with hole. There are many such cases in which there are discontinuities. So without discontinuities, there can be no machine part. So therefore, you have to have this discontinuity. Okay. So the first example was a plate with hole and average area. You take it at this section here. So introduce a plane over here and so similarly here in the second example. So this is the least cross section. This portion here. Okay, so along this portion the crack will start over here and it will propagate. So that is why we consider this as the least area portion. Similarly, in all examples, wherever the least area or the discontinuity starts, so that is where we determine that it will start breaking at that particular point, right? So in here we consider this as the least cross sectional area. Okay. So we'll solve problems on this. So in case of in the data handbook, how it will be given is you will have this diagram given along with the value of KT. What is the maximum amount of stress, or we can find what are the dimensions of that particular plate. We can find using this, and also we can find what is the average stress and all those things. Right. So this is how we find out. Okay, so we'll start solving some numericals on this. Let's see how we can find out. We check out this first problem. So you have a steel plate of width 50 mm, thickness 10 mm, with the hole of diameter 10 mm. So actually this figure is not given. So this is in the solution part. We need to find out the value here. Using the values, you have to draw the figure and and solve the problem. So steel plate of width 50 mm. So steel plate of width 50 mm thickness, 10 mm 10 mm thickness, 50 mm width, and the hole of diameter 10 mm drilled at center, subjected to tensile load. And by taking the stress concentration factor into account, maximum stress in the member is 60 Newton per mm square. So maximum stress is already given. So let's see how we can solve this. So this is our question here. We have our question, and given what is given is, the maximum stress sigma max is given as 60 newtons per mm squared. So 60 newtons per mm squared is given, and what is asked is you need to find the force, the tensile load F. What is the tensile load F which is acting on this particular material? And width is given as 50, and diameter of hole 10 mm, width 50 mm, diameter 50, and height is also 10 mm. Height is nothing but thickness. Thickness is 10 mm. So if you want to know what is W, what is D, what is H, you can head on to the data handbook. I'll show you the data handbook. It is in the 4th chapter for your information. Okay, see here. So there are a series of figures. So you need to refer to those particular figures which give you the diagram, and also the the graph. As I told you in the previous slide, you need to refer to the figures first. There are plenty of figures with respect to each type of discontinuity. We have plate with hole, plate with shoulder, and plate with cylindrical plate with hole. All formulas relating to that you will find out that particular sheet itself. So check this out. So we have W and D, and you see H is the thickness. Okay, the side view. Side view is not given, but you can see the very next figure. H is as thickness. So whatever notations I'm writing, these are I've taken it from the data handbook itself. So W, D, and H. If you don't know what to write, so W, D, and H is nothing but the thickness. So you can see formulas are also given with respect to that particular diagram and stuff. Okay, you got it. So let's write the formula. So formulas are also here. So this is from figure 4.5. So you can see figure 4.5. Refer to that particular figure first. Okay. So let's see the solution. Solution from figure 4.5. So this is from the data handbook. You see, from the data handbook, I've extracted these values. So what is the formula is also given. So see, K sigma, that is the stress concentration factor, is sigma max by sigma nominal. Okay, K sigma, the stress concentration factor, is equal to sigma max by sigma nominal. That is a nominal stress value. Also, sigma nominal is also given for you. Sigma nominal is F, force by W minus D into H. F by W minus D into H. So here we don't know force. We know W, we know D, we know H. We also know sigma max, right? But K sigma is yet to be known. Okay, so first let's substitute and find what is the value of nominal stress, or find the value for K sigma and plug this value in here to get the force F. So, but we need to get K sigma first, right? So we want nominal stress to be supplied from here to here. So nominal stress we want it from here to here, but we need K sigma first. So let's do that. So sigma nominal, there is nominal stress is equal to sigma max, maximum stress, by K sigma, that is stress concentration factor. So where will you get stress concentration factor? We need to go back to data handbook. So check out the data handbook. You have K sigma value over here. Okay, so that means we need to find what is the value of dW. See the x-axis here. You can write over here. So you see here in the x-axis, you have this d by w. So d by w, you need to extract from the diagram. So d by w is equal to what? So d is from the data, it is 10, w is 50. So this is d is 10 by 50. So that means if you cancel out, you get 1 by 5. So what is 1 by 5? 1 by 5 is 0 0.2, right? So d by w is, this is 0 point, difficult here, 0.2. Okay, so 1 by 5 is 0 0.2. So for 0 0.2, whatever corresponding value you have, so you need to go above straight this line. Okay, so wherever it intersects the curve here, so from there you need to draw back another line. Okay, somewhere here you are getting. So wherever that 0 0.2 line coincides with the curve and comes back along the same line to the x-axis, that is your value of K sigma. So K sigma here I can say is somewhere between 2.4 to 2.6. So this is halfway is 2.5. I'll just write 2.52 something approximately. Okay, approximately you can write wherever it intersects. So you can choose a little bit of flexibility here. So I'll write 2.52. So I hope you are able to grasp this. I'll repeat this once again. See, this is we need to get the value of nominal stress. For that, K sigma is required. K sigma, you'll get it from the y-axis, but x-axis is d by w. Okay, you need to do that d by w manually and solve that. So 10 by 5 is 0 0.2. So for 0 0.2, you plot back on the x-axis, from the x-axis to y-axis, and wherever it intersects, that value will give us K sigma. Okay, from this figure, you need to make it out. So I'll write here K sigma. Sigma max was 60 megapascal or Newton per meter square. 60 by K sigma, I'll write 2.55. So once I get this, I get my nominal stress. So sigma nominal, I get it from this here. That is what is the stress at the cross section? It's the plate with the hole, right? So I have my hole like this. Okay. So this is the cut portion of the plate. So this area I'm trying to, this is what stress is being applied here. So that is the nominal stress. So what is the stress at this area? That is what is giving me the nominal stress. So find the nominal stress, give me the value, and along with this, now once we get the nominal stress, now we can plug this here. So you can plug the nominal value, whatever we get over here, and that will be equal to F by W. W is width, it was 50 minus diameter 10 and height also 10. Okay, so we got 23.52 newtons per mm square. So we'll plug this value here, is 23.52. Now we'll get force out of this F. So 50 minus 10 is 40, 40 into 10 is 400. 400 into 23.52. You just calculate this, let me know the answer. $400 into 23.52. We got somewhere like 9408. We got force as 9408 newtons. Okay, so that's our answer. Okay, this is our answer. What is the force required from the we have solved? I think that was what asked in the question. What is the tensile load F of the member? What is the load applied? So this is how the procedure it follows.